All right, welcome to our first video on the topic of linear systems. So to do a quick warm-up, we're actually going to sort of do a quick review of some stuff from the very first part of class. So I just want you to solve these as quickly as possible. All of these note are y prime equals some function of t times y. So really, I just sort of want you guys to remember what the form of functions like this look like. So try to do it as quick as possible. If you can remember the formula, just use it. But yeah. Okay, let's go over the answers. So remember, if we have something like this, the formula is always some constant c times e to the integral of ft. So for this one, we're going to have y equals c e to the 4t. Number b, we're going to have y equals c e to the negative 3t. Here, y equals c e to the t squared. And here, if we move it over to the other side first, we're going to have y equals c. Oops, I am on the wrong notes. Should just be t squared. All right, this one, a little bit trickier, but it's also something we're going to sort of be working with today. So let's do a quick recap. So remember here, what we want to do is we use this integrating factor mu. So this is e, and then we just the integral of negative 6 dt. This time we don't care about the constant because this isn't going to be our final solution. So we're going to get e to the negative 6t. We multiply that to both sides. And on the left-hand side, assuming we did the integration properly over here, we have the derivative of e to the negative 6t times y, and then equals e to the negative 6t times e to the t plus e to the 6t. Simplifying that a little bit, e to the negative 5t plus 1. And now to get rid of the integration, we just integrate both sides. Here everything just cancels. Here we get e to the negative 5t over negative 5 plus t plus some constant c. And now just solving for y, we get as our final answer y equals e to the t over negative 5 plus t e to the 6t plus our constant c times e to the 6t. All right. So hopefully you were able to solve those. If not, hopefully you sort of remember how to do it after I did it, because we're going to sort of be dealing with these types of problems again. So today we are going to start talking about, well, systems, but really we're really only ever going to do linear systems. And at the end, we're really going to focus on linear systems with constant coefficients. So just because, for whatever reason, I like tying things back into basic algebra, you might remember when you were first learning about algebra, you probably didn't even use letters. You had like a question mark, like 2 plus question mark equals 5. And then you saw, okay, it's 6. Soon after that, you got to variables, 2 plus x equals 5. But then a little bit after that, they started introducing, multiple variables. So maybe 2 plus x equals y. and y minus 1 equals 4. And so today, this is a system of equations because there's more than one and they're sort of interconnected in some way. So today we're going to start looking at systems of equations, and where our equations are differential equations. So as always, we'll start with a real basic example. So we're given something like this. So if we have an equation like this, right, notice that the y, sort of one equation involves only y's, the other equation involves only x's. So this is what's known as an uncoupled system. And solving these is very straightforward. There's really no extra work, or it's not any harder. It's just, you're doing it twice. Y equals c1 e to the 6t, and x equals c2 e to the negative 4t. So note sort of the one important thing is that we are going to have two constants here. Like we can't just use 1c because that's not going to have all the solutions, right? Because if y is e to the 6t and x is twice e to the negative 4t, that's going to be a solution, so we have to have sort of two different constants there. So not going to really spend much time on uncoupled systems. Let's look at something which isn't uncoupled, but we can still solve. So let's solve x prime equals 2x minus 9y, and y prime equals 5 times y. So you might look at our first equation and seem that it still seems actually maybe sort of a little bit hard. But here, if we start with our equation involving y prime, it's very straightforward. We can see right away, sort of using that formula, okay, y has to be equal to some constant, which we're going to call c1, times e to the 5t. However, now that we have solved this, we can go back and solve our first equation. So x prime equals 2x minus 9y, where y is this thing. So this is first order linear at this point, so it's pretty straightforward. We give our integrating factor. So e to the negative 2t times x, the derivative of that is equal to negative 9 c1 e to the 3t. We integrate both sides to get e to the negative 2t times x equals negative 3c1 e to the 3t plus our other constant c2. And now we see that x of t is equal to negative 3c1 e to the 3,2 plus, oops, wait, not e to the 3,2, e to the 5,2 plus c2 e to the 2t. and I'll just rewrite y so I can circle it and have my final answer. All right. So hopefully, maybe still getting accustomed with these first order linear equations, the integrating factor stuff, but pretty straightforward stuff we have done before for the most part. One point I do want to make is note, in the past, anytime we've sort of had a constant, if we have something in front of the constant, we try to make just every order, we try to just sort of make the constant as simple as possible. So we always try to absorb constants inside. If it's an arbitrary constant, we have to be real careful about that here, because even though C1 is an arbitrary constant, it shows up in two places. So C1 is an arbitrary constant, but because it shows up in two places, if we change it in one place, we have to also change it in the other. So if we did want to absorb that inside, we could, but it probably wouldn't make our final answer easier, right? We could multiply this constant by -3, but then we would have to divide it by -3 over here. But we always have to do that. We have to make sure that the constants sort of could represent the same thing. All right, let's look at a slightly more complicated example before I end this video. All right, so again, with this, if we look at it, we see that this second equation with y prime equals stuff has both an x or a y and a y in it. So it's probably good to start here. So we'll rewrite it x prime plus 3 over t times x equals 15t. Our integrating factor is going to be t cubed. And so we're going to have the derivative with respect to t of t cubed times x is equal to t cubed times 15t. We now take the derivative, and we get t cubed x equals 15t to the 5th divided by 5 plus some constant c1, or x is equal to 3t squared plus c1 over t cubed. All right, we can now go back and plug this data into our second equation. So we have 3t squared plus c1 over t cubed minus 4 over t times y minus 7t cubed. So this is going to be 3t cubed minus 7t cubed gives us negative 4t cubed, and then plus c1 over t squared. Our integrating factor is going to be t to the fourth. And so we have the derivative t to the fourth times y is equal to negative 4 t to the third times t to the fourth is t to the seventh, plus c1 t to the fourth over t squared is t squared on top. Oh, and I've dropped the c1. Careful not to do that. T to the fourth y equals negative 4t to the 8 over 2 plus c1 t squared over 2 plus some other constant c2. So finally solving for y over there, we're going to get y is equal to negative t to the fourth over 2 plus c1 over 2 times 1 over t squared plus c2 over t to the fourth. Okay, so this would be our final answer, both of these together. And I'll just note again, there are still things you can sort of do with these arbitrary constants to maybe make the answer a little bit nicer. One option here is I sort of, I want to get rid of this divided by 2. So C1, 2, I'll call this C1 prime, is the old one, over 2. That's kind of confusing. Okay, I want to introduce a new constant, C3 over C1, something like this just to show a little bit more. In that case, C1 equals twice C3. And so I could rewrite this equation now, x equals 3t squared plus 2c3 over t cubed, and y equals negative t to the fourth over 2 plus c3 1 over t squared plus c2 over t to the fourth. Except now, it's weird, there's just c3 and c2, so I just call it c1 again. So this is an alternate answer, which is totally correct, just a slightly different way of writing it. Either way is fine. If you want to be real safe, you could just really not absorb any constants inside your C1 and C2. All right, let's end the video here after an exercise. So we're going to look at the following systems. System 1 is going to be x prime of t is equal to 4 times x, and y prime of t is equal to 2x minus 7y. And for our second exercise, we'll have x prime equals y plus 3 over t x minus 4t to the fourth, and y prime is 1 over t times y of t plus 12t cubed. Right, so give those a shot. It should be clear sort of here, you want to start with this system because it doesn't have any y's, and here you want to start with this system because it doesn't have any x's. Yeah, pause here, give it a shot. All right, and now I will just write down the answers. So for this first one, we're going to have x is c1 e to the 4t. Hopefully everyone at least made it that far. And then if you didn't adjust your c1 at all, you should have gotten 2/11 c1 e to the 4t plus c2 e to the negative 7t. All right, so for the second one, you should have solved for y first and gotten c1t plus 4t to the 4th. And then using that info, x2 would have been negative c1t squared plus c2t cubed. And just to make this point one more time, I'll write down an alternate answer if you wanted to try sort of adjusting these coefficients. What you could do is just sort of, to get rid of this 11, replace c1 with 11 times c1. So x of t equals 11 c1 e to the 4t. Y of t equals 2/11 times 11 c1 e to the 4t plus c2 e to the negative 7t. And of course, you probably wouldn't express it like that as an answer. Just cancel out the 11, and you have 2 c1 e to the 4t. Right, we will end it there.